Welcome to This Explainer. Today we're diving straight into a mind-bending chronological journey. We're going to track exactly how ordinary, everyday beach sand becomes the cutting-edge hardware powering the entire AI revolution. Seriously, it's an engineering marvel that tests the absolute limits of physics, and is happening right now as we speak.
But first, let's talk about a pretty staggering price tag: $30,000. That's the estimated cost for just one single blank 2-nanometer wafer produced by TSMC. And get this, that's before it even gets chopped up into individual chips. Reaching this incredibly valuable starting line takes thousands of painstaking steps and over 3 months of continuous processing inside ultra-clean factories.
So how do we get there? Well, the journey kicks off with quartz sand. But not just any sand. It has to be chemically purified until it hits an almost unimaginable 99.999999% perfection. That electronic-grade silicon is then melted down and grown into a massive 100-kilogram single crystal we call an ingot. From there, a highly specialized saw slices that heavy crystal into individual wafers that are barely 1 millimeter thick.
It's wild to think about. We're taking literal dirt and transforming it into a flawless, mirror-smooth blank canvas. This shiny disk is the absolute physical foundation for the smart technology and AI models we all rely on every single day. Without this exact canvas, no ChatGPT, and definitely no AI boom.
Which brings us to Section 1, the magic of EUV light.
Okay, before we can carve even a single transistor into that blank disk we just made, we need a light source unlike anything found in nature. To print circuits way too small for the human eye, imagine this crazy high-tech sequence inside a vacuum. Falling drops of molten tin are being repeatedly blasted by a high-power CO2 laser. It vaporizes those droplets 50,000 times every single second. Just let that sink in. 50,000 tiny, controlled explosions per second, all just to create the light that draws the lines of an AI chip.
And that process gives us extreme ultraviolet, or EUV light. It operates at a microscopic wavelength of just 13.5 nanometers. That's practically in the X-ray range. Because this light is so incredibly fine, it creates lines 14 times sharper than the older deep ultraviolet machines. It literally allows engineers to print details roughly the width of just 40 silicon atoms lined up side by side. We are talking about the absolute bleeding edge of Moore's law here.
So once that EUV light is cast through a stencil-like mask, we hit the etching step. A blue photoresist acts like a protective shield for the wafer, and the unexposed areas are washed away by chemical solvents. That perfectly carves out the underlying materials to create the transistor. This gets repeated layer after layer, slowly revealing the invisible, nanoscale 3D architecture of the chip. Now you might be wondering, who actually makes the machine capable of pulling this off? Well, this vital process relies almost entirely on one single company in the Netherlands called ASML. They hold a massive 94% global monopoly on this market, and they sell their newest high-NA EUV machines for around $400 million each. That is the price of an actual skyscraper for a single machine just to handle this atomic-level printing.
Moving on to Section 2, AI-powered chip design. Designing chips with billions of tightly packed transistors has become a puzzle that human engineers just can't solve on their own anymore. So, semiconductor developers use AI-enhanced electronic design automation, or EDA software. These tools leverage machine learning, specifically trial-and-error reinforcement learning, to seamlessly optimize 3 crucial metrics: power, performance, and area, or PPA for short. These AI agents run endless simulations to make sure the chip runs incredibly fast without overheating or wasting any valuable physical space.
The engineering firm TestSolve sums it up perfectly. They note that these tools excel in navigating the multifaceted design space, aiding informed decisions on power, performance, and area trade-offs. It's pretty incredible to think about, right? By using AI to explore this vast design space, engineers can simulate real-world behavior and catch errors early on. This prevents massively costly manufacturing mistakes long before a single chip is ever physically built.
Next up, Section 3, Rethinking Deep Learning Scale.
Once we actually manufacture these dense, perfectly designed chips, we face a whole new problem. Traditional distributed GPU clusters are wildly inefficient at training the absolute largest state-of-the-art AI models. Chaining together 540 traditional servers, that only yields an 89 times speedup. The returns drastically diminish.
And why is that?
Well, as you add more and more GPUs, those devices end up spending most of their time navigating complex communication roadblocks and waiting on data to travel over cables, rather than actually crunching the numbers.
So instead of building a fractured, highly complex cluster of thousands of chips, a company called Cerebras solved this by building the wafer-scale engine. They densified an entire cluster onto a single massive chip, packing 850,000 AI-optimized cores. They use an ingenious method called weight streaming. Think of it like keeping the workspace completely clear while instructions are fed in line by line, completely bypassing those traditional communication bottlenecks. It's a real game changer.
Finally, Section 4, Assembling Exascale Supercomputers. All of these physical and intellectual innovations, the flawless silicon, the atomic-level EUV etching, the advanced AI architectures, they all culminate in our final act. Behold El Capitan. Housed at the Lawrence Livermore National Laboratory, it takes up 7,500 square feet of floor space. That's roughly the size of 2 tennis courts. This $600 million behemoth utilizes over 44,000 interconnected AMD devices, sharing memory seamlessly across CPUs and GPUs. It requires 30 megawatts of power to run, and in return, it delivers a staggering 1.8 exaflops of computing power for the U.S. Department of Energy to run highly sensitive stockpile simulations, model climate change, and even find new medical cures.
As we wrap up this explainer, looking back at the monumental leap from a simple, purified grain of sand to a 30-megawatt exascale supercomputer, we have to ask ourselves a vital question. As accelerating hardware engineering continues to test the absolute boundaries of physics, what impossible global problems will the next generation of AI chips finally allow us to solve? Thanks so much for joining me on this incredible journey, and keep questioning the technology that shapes our world.